Hello and welcome to this video presentation on the basics of power factor correction. My name is Martin Hlavačka and in this video I will talk about power factor correction and the types and modes of compensation. In this video I will talk only about the theory of power factor. The calculation of power factor and reactive power will be covered in another video. Active power is the real power transmitted to loads such as motors, lamps, heaters, and computers that is transformed into mechanical power, heat, or light. Reactive power is required to produce the magnetic fields that allow real work to be done. It is supplied by inductive loads such as motors or transformers due to its inherent property of inductance, which causes the current to lag behind the voltage waveform, resulting in a phase shift. This lagging current creates reactive power. This reactive power then circulates between the source and the reactive components. Inductive load that has a low power factor requires generators, transmission and distribution systems to pass reactive current, causing a 90-degree lag in system voltage. Reactive power generates electric and magnetic fields that cause reactance in the line. For the grid, this results in an increase in line current for a given active power transmitted to the loads. The consequences are the need to oversize transmission and distribution networks by utilities, increased voltage drops along distribution lines, and additional power losses. For the industrial consumer, this translates into an increase in electricity bills due to increased overall apparent energy demand, increased power consumption within the premises, penalties applied by most utility companies on the reactive power and the reactive power in the facilities also has the other consequences such as the overload of the transformers, increased temperature rise in power cables, etc. Since we covered what active power and reactive power are, we can explain apparent power. Apparent power is the total power supplied to the load. Apparent power determines the size of equipment such as transformers and generators. It is the root mean square product of voltage and current in an AC circuit. Power factor is a measure of how efficiently electrical energy is used in a system. It is the ratio between the active power and the apparent power flowing to the load from the source. The power factor value will range between 0 and 1. In the best case, it can be equal to 1. Most loads are inductive, meaning the power factor will typically be less than 1. The power factor shows how much of the total supplied current is used to do real work. A power factor close to 1 means that the apparent power is minimal. This means that the rating of the electrical equipment is minimal for the transmission of a given active power to the load. The reactive power is then small compared to the active power. The further the power factor is from 1, the greater the apparent power supplied and therefore the greater the current supplied to the system. On this slide, we can see the typical power factor value for different types of electrical equipment. Understanding the power factor relationship helps you better manage reactive power rates and reduce business demand charges. If the facility's power factor is below 90, 95 and 96%, the utility will typically charge a reactive power fee. The solution to this is power factor correction. It can also be called reactive power management. Power factor correction, which is to generate reactive energy at the load level to avoid unnecessary current circulation in the network. This is achieved by connecting capacitors which produce reactive energy in opposition to the energy absorbed by loads such as motors. Capacity loads, such as capacitors, create reactive power due to their inherent property of capacitance, which causes the current to lead the voltage waveform, again resulting in a phase shift. This leading current creates reactive power. Before implementing power factor correction, an inductive load that has a low power factor requires generators and transmission and distribution systems to pass reactive current with associated power losses and exaggerated voltage drops. After the implementation of the capacitor bank at the load level, its capacitive reactive current will take the same path through the power system as the load reactive current. Since this capacitive current is in a direct phase opposition to the load's reactive current, the two components flowing the same path will cancel each other out, so if the capacitor bank is large enough, there will be no flow of reactive current in the system upstream of the capacitors. The installation of power factor correction equipment in the facilities allows the consumer to reduce their electricity bill by maintaining the level of reactive energy consumption below a value agreed contractually with the power supply authority. But in general, it is not economical to fully compensate an installation. Depending on the tariff, the power supply authority can deliver reactive energy for free. It may be also found that it is more economical to provide only partial compensation and that paying for part of the reactive energy consumed is less expensive than providing 100% compensation. The question of power factor correction is a question of optimization, except in very simple cases. Improved business performance is one of the benefits of power factor correction. CAPEX is reduced due to lower equipment cost. OPEX is reduced by reducing power losses, reducing subscribed power, and eliminating reactive power penalties. Reduce the installation size of transformers, switchgear, and cables. Sizes are determined by electrical current requirements, so reduced current means less expensive equipment that is easier to install. The reduction of total CO2 emissions is another advantage. Electricity bills are typically reduced by 5% to 10%. For this reason, the payback on the investment in power factor correction can be in only 1 or 2 years. Reducing power losses is another advantage, as it helps prevent overheating of transformers and panels. Reducing or even completely eliminating the reactive power in the upstream conductors, thus reducing or eliminating voltage drops. Increasing available power by improving the power factor of a load supplied from a transformer, the current through the transformer will be reduced, thus allowing more load to be added. In practice, it may be less expensive to improve the power factor than to replace the transformer with a larger unit. The power available thanks to the implementation of power factor correction can be increased by 30% or even more. Different types of compensation can be implemented depending on performance requirements and control complexity. It can be fixed, automatic, or dynamic. The fixed compensation type uses one or more capacitors to provide a constant level of compensation. Control can be manual using a circuit breaker or switch disconnector, or semi-automatic using a contactor, or by direct connection to a device and switched with it. These capacitors are installed at the terminals of inductive loads or on a bus bars that supply numerous small motors and inductive devices for which individual compensation would be too costly. Automatic compensation provides automatic control and adapts the amount of reactive power to installation variations to maintain the target cost field. Control is usually provided by static contactors. The equipment is applied at points of an installation where the variations in active or reactive power is relatively large, for example on the bus bars of a main distribution board or the terminals of a heavily loaded power cable. The dynamic compensation type associates a fixed capacitor bank and an active electronic compensator providing either leading or lagging reactive currents. It is necessary when there are fluctuating loads and voltage fluctuations must be avoided. It provides fast, continuously variable compensation that is perfectly suited for large industrial loads such as elevators, crushers, spot welding, etc. Let's talk a little more about the type of automatic compensation. A capacitor bank is divided into several sections, each of which is controlled by a static contactor. Closing the contactor puts its section into operation in parallel with other sections already in service. Therefore, the size of the bank can be increased or decreased step by closing and opening the control contactors. The automatic compensation type consists of a control relay that monitors the actual power factor and commands the connection or disconnection of capacitors to obtain the target power factor. The reactive energy is thus controlled in steps. In addition, it provides information on the characteristics of the network like voltage amplitude and distortion, power factor, real active and reactive power, and the status of the equipment. Alarm signals are transmitted in case of malfunction. The current transformer from the control relay must be placed on one face of the incoming cable that supplies the circuits being controlled. Static contactors are especially suitable for a certain number of installations that use fast cycling equipment or installations sensitive to transient overvoltage instead of conventional contactors. Its advantages are an immediate response to all power factor fluctuations, an unlimited number of operations, the elimination of transient phenomena in the network when changing capacitors, and completely silent operation. The location, the place of connection of capacitor banks in the electrical network is determined by the general purpose, the mode of operation, the foreseeable influence of the capacitors on the characteristics of the network, and the installation cost. The location of the low voltage capacitors in an installation constitutes the compensation mode, which can be global, by sector, or individual. In the case of global compensation, the capacitor bank is connected to the bars of the main LV distribution board of the installation and remains in service during the normal charging period. This configuration is suitable for a stable and continuous load factor. It is very cost effective, but the reactive current still flows in all cable conductors downstream of the LV main distribution board and offers limited flexibility to cope with numerous loads turned on and off throughout the day. In the case of compensation by sector, the capacitor banks are connected to the bus bars of the secondary distribution panels. An important part of the installation benefits from this arrangement, in particular the power cables from the main distribution board to each of the local distribution boards where the compensation measures are applied. Other advantages are that losses in the cables themselves will be reduced and is cost effective compared to local compensation, but typically requires automatic power factor correction. However, reactive current still flows in all cables downstream of the local secondary distribution boards, and when large changes in loads occur, there is always the risk of overcompensation and consequent overvoltage problems. In the case of individual compensation, the capacitor banks are connected directly to the terminals of an inductive load, which are generally motors. This configuration is very appropriate when the load power is significant compared to the contracted power. Its advantages are that it reduces the size of all cables as well as their losses. It is the best technical solution because reactive energy is supplied where it is needed and there are no longer significant reactive currents in the installation. However, this type can be expensive depending on the number of inductive loads. We come to the end of this presentation. Now you know the basics of power factor and power factor correction. Thanks so much for watching. Stay tuned for the next video where I will talk about the effects of harmonics on power factor correction solutions.